Okay, time to start class. I see everyone here except for James. Just to make sure that everyone knows, I did fix the link to OneNote. If you want to look at the lectures we've done in the past, or look at the pages where people have solved the problems at the beginning or end of class, and following the link that I emailed at the beginning of class didn't work for you, you can always go to, and yeah, this is the right class. Go to the class site on Moodle, and down here at the bottom of lecture materials, before chapter 1, you have the OneNote classroom for Physics 151/251, and that will take you to a web page version, which you can from then bring it into your desktop version if you want. Oh, great. It's kind of interesting that worked. It was because I was not, or didn't work, because I'm not logged into Moodle, not because I'm not logged into the other resource. Come on now. Okay, yeah. So here it's bringing up OneNote, so you can see the things that are available there. Depends on how fast the internet is going, I suppose. So you can look, here's the lecture that I'm going to be going over today without my notes on it because I put it up before class. If I put it up after class, which is what I usually do, then you would see the notes I did in class and so on. So just want to make sure people are aware of that resource being there. I'm actually going to close this now because it'll probably take up more computer resources than I want it to. And go to the presentation. Actually, not even go to the presentation. I'm going to go to here. Problem, I told you last class period that I would, instead of a homework problem, have this be what is solved at the beginning of class because we didn't have time to do it. It's down to 2 groups. I better put it this way. So whichever group is not today, guess what you're doing on Friday. So it is Lydia, Sarah, Emily, and Madison. And as you know, on Friday it's going to be Mira, James, and Kaylin. So we're not going to watch the video again. There's the numbers, and I don't have the question written here like I had before, so I will write down. So you're answering those 2 questions. Have at it.
I will draw as long as people tell me what. Oh, this was weird. Okay, first things first. What do you want me to do?
I don't know. Will the car be in the air? So we have to look at the equations. Can we look at your equations?
I have equations.
Oh, I'm doing it. Okay.
And what chapter are we in? Or does it not matter?
Okay, draw a picture.
What am I drawing?
A car and some incline. Give me it.
Oh, you're left-handed.
Nice. And then a box is going to be our car.
Oh, yeah.
Put some little wheels. Nice.
And then, I don't know. Here.
What does it mean by 10 feet easy?
That's what he said. He said, if we go 50 miles an hour, we'll make 10 feet easy.
Okay.
That's a quote from.
So how
Okay.
fast is it going to go?
Just
75
go with
miles
the.
75.
Choose whichever one. I don't really care.
So
Okay.
75 would be our initial.
So I can just exit that out. So our initial speed is 75?
Mm-hmm.
Okay.
What do you think we would do? In this one, right? No.
We're looking for.
So we have mass and initial velocity, and we have the.
Could we not use something like this?
Wouldn't you be doing these things?
Or is it? Yeah.
Find
The question: how long will the car be in the air? So we need to find for seconds or like a time. So it needs to have time in it. So we need to find time. That's a question mark. And we know what our theta is.
30.
Oh, where's the erase button?
How do you erase?
Found it. What was I on?
Purple.
Oh, turn the pen over. Just use the backside of the eraser.
That's cool.
That's theta. Okay. And then we have our mass. So
we need to convert it probably, and the velocity too.
Is that mass or weight? Because then we have to put a force of gravity on it, and then.
yeah. We can go weight and we can find it for that. So weight divided by gravity equals mass. No? Yeah?
How do we convert it to grams? Or, yeah, grams.
What's the gravity? Units.
Meters per second squared, but we need to convert it to grams.
This to grams?
Yeah. Instead of pounds. I don't know conversion.
What's the conversion to pounds to?
Or do we not need to go there?
Is I don't remember because we never use it. Let me help you out.
Okay.
Have we ever used the weight when we were talking about trajectories?
No.
No. That was immaterial. This was a movie, and the guy is supposed to be a physics major, but
So we can basically ignore that.
so that's an unimportant detail.
Okay, so we just need to find the
Unless you're taking the
The time.
distance.
I think we need to find the distance
Since
first to find out how long it'll be in the air.
okay.
So start with the second question.
This question here. How far will it clear? Okay.
Because if we only have velocity,
So-
we can't figure out how long.
Clearing. He's talking about position.
We have this little river, and then we have a landing. So we need to find this distance.
So that will clear 10 feet. So that's our.
How far will it clear is 10 feet?
Well, that's how much he thought.
That's what he
actual
thought.
distance. They just.
But I think we just
guess.
ignore that, right?
Yeah, that's just his estimate.
Which one?
So we're looking for.
Does somebody want to offer them some advice?
Yes, please. Cool. Thanks, guys.
Because we have velocity, and it's going like this, so you need x and y to find that.
You think we're doing this?
Yeah, no, this right here. So like velocity times cosine 30 for the x, and then velocity times sine
What's our
But we would
velocity?
need
for the y, and then do this.
Our velocity
And that
is
would be our-
Do we have to convert the miles per hour to meters per second?
Yeah.
What's the conversion for that?
I don't know if it's like 4% or something like that.
Maybe try using range equations.
Okay.
Yeah, actually it is 0.447. So 1 mile per hour is 0.447 meters per second.
1.44?
Yeah.
What is it?
0.44.
Put in 0.75.
33.53.
Okay, and that is our.
Velocity.
So they said range equation. Oh, I love
Is
this.
this
I need one.
This one. Is this the ring?
Yeah.
So just the initial velocity squared.
Running out of room here. I'm gonna erase this.
So we just rewrite this because we have everything.
33.53
What is it?
squared.
Mm-hmm.
So the range is what? We're figuring that out.
Velocity squared. So 33 squared.
And the angle is
Times
30.
sine 60 over 9.8 meters per second squared.
Oh no, I was reading that.
So it's about 10 feet. It's not 10 feet. Meters.
Okay, now.
We got the second question.
Oh,
And
yeah,
then
that's the second, not the first. Sorry.
And then how long will it be in the air?
probably that.
This one here.
Yeah. Because delta x equals vt. So t equals delta x over v. Rearrange it.
I see what you're saying. This here. Okay, that's over here.
Mm-hmm. No, just
Just this.
rearrange that. So we're
Rearrange.
using for t.
So
Like
it's
if
just
you
gonna
move
be.
x not over to the other side, it's delta x.
So it needs to be set to
Yeah.
to t.
T equals.
Okay.
So
Delta x over v. And you know delta x now. Then we know velocity.
What's your delta x?
is
What we
the
just
9.
solved, 9.87.
Over our velocity, which is the what's our 33.53.
Wait. 9.87 33.53 is 0.29.
Now, there's one problem. The first one, I assume, is right. I don't remember the number. The second one has a problem. Anybody see the problem in that? Help them out.
You guys are now meters per hour, meters per second, velocity is meters per second.
We have
The units are fine.
Okay.
Do we need to use acceleration?
acceleration
Nobody sees the problem?
I'm talking about that equation.
Is the time
The other
actually
ones
the
have
time it
acceleration.
gets across? Oh.
Oh, you think?
So I don't know which other equation it would be.
Maybe it's that one. I think it's that one actually.
This.
And it's
Self
just going with gravity.
There's gonna be something like this. We need to find that time that it's in the air.
So, oh, that's right. You need to use the component in the horizontal direction because you're only talking about the horizontal distance traveled.
Right.
Oh,
And so you
maybe.
have to, instead of using the 33.53 meters per second, you need the horizontal component of that speed.
Oh, that makes sense. Okay, so which one is the horizontal? That's the one. Okay. So. I need a problem.
You can't scroll more.
Mm-mm.
Oh.
There's stuff down there. Just trust me, there's stuff down there. Okay, it's AX.
So it would be 30 cosine. Or no.
No, not 30 cosine. What's this number here then? The
Hour.
9.87?
Cosine 30.
Mm-hmm. So then we can do this. Yeah, do that.
You put the distance times cosine instead of speed times cosine.
So the speed would be still 33.53.
The speed is 33.58 meters per second. You want to find the component of the velocity that's the horizontal speed.
Oh.
So you take that speed times cosine 30. That tells you horizontal portion.
So it's that 33.53 cosine 3. Yeah. Now I can put this here, right?
Okay, that, assuming all the math is correct, that should be correct.
Yeah.
Ryan appreciates your work.
I did.
Okay, so there is a solution for you. Now, there's more than one way to skin a cat, so I'm going to show you two other ways of doing this. But first, I'm going to make a statement. You haven't seen me use this equation in class, right? It's in the textbook, but I didn't use it in class. The reason is that equation only works in the special case of the starting and ending points being at the same elevation. If they're not at the same elevation, it's not going to work. So in this problem, and I intended for you to make this assumption, you assume that the starting and ending elevations are going to be the same, so the equation should give you the correct answer. But in general problems, such as the one I'm going to work out after we finish this equation would be useless to me. Looking at the time, I'm not going to have time to do the full-on solution for well, I probably will anyway, cut off some other things. Okay, so how else could we have solved it if we didn't use the range equation? Break into components. That's our first step. So I have to define my directions if I'm going to break it into components. I can't break into components if I don't define the directions of my components. And so I had, as they did, 30 degrees. Here's my speed in the x. Here's my speed in the y. These are both initials. Here's my speed initial equals, and leaning on their work, 33.53 meters per second. MPS, I know what you meant there. It's not a standard for meters per second because there's confusion between miles per hour and miles, and that could be. So normally we would have put this conversion factor with a m/s on top and then mph for miles per hour on bottom. And you notice the miles per hour would cancel that. Okay, so coming back to this, they've already calculated, because the x coordinate is the adjacent side of that triangle, then vx0 over v0 is cosine theta, or vx0 is cosine, well, put that in the wrong order. And they did the calculation for me of 29.04 meters per second. Whoops, that's the color they did. Trying to keep it separate. Vy0, that's the opposite side of the triangle. So which trigonometric function relates opposite in hypotenuse? Sine 30 degrees is a wonderful angle because sine of 30 degrees is 1/2. So all I have to do is take half of 13.53, and that's going to be 765 meters per second is the initial velocity in the y direction. So I've broken it into components. Now I need to find the time in the air. Usually in a problem like this, we turn to the y components to find that answer. And this is the usual case. So I'm going to look at the y components. I usually actually take these problems and put the x components in the y problems. I don't know how far it's going to travel. I'm going to find that. So there I have broken down, I have two problems, the x problem and the y problem. The thing that ties them together is time. Now, if I look at this, time is unknown. So if I look in my x column, I have two unknowns, time and x final. If I look in my y column, I only have one unknown, time. So that's where the genius in me says, I'm going to go to the side with only one unknown. I use genius facetiously, of course. So let's do that. Taking the y, what equation should I use? What variables do I have? Y, V, A, I'm looking for T, that's 4. That is all of them. So I'm going to use the equation that has all of them, so I'm going to use put in my that's 0, and I have I replaced AY with minus G. Since I have T's in both of these, I can cancel out a T and get an equation that says I moved it to the other side of the equal sign. And so I added, I'm sorry, I should have not done two steps at once. So I added GT to both sides, GT over 2, excuse me, to get GT over 2 is equal to VY0. Therefore, time is equal to 2 VY0 over G is equal to 2 times 16.765 meters per second divided by 9.80 meters per second squared. And now we'll have a double check on their answer, right? 2 times 16. And it's actually a much bigger number. So I have 3.42 seconds is the time it's going to stay in the air. Now, of course, that is, let me make sure I didn't make a mistake with dividing by 2. I just want to double check rather than go out and say, Okay, so yeah, that was right. So the time in the air, actually 34.2 seconds. Now, what if you didn't like that result and you wanted to check it? You can always go back to your problem and check with your numbers. I'm instead of going to go check it, I'm going to solve it a different way. I'm going to solve it a different way because we know that in the absence of air resistance, when something's flying through the air, the motion up is symmetrical with the motion down. So that means at the same elevation, you have the same speed. It's just the vertical direction is opposite. So I could have taken my y data, a variable I did not write here, but I could have said Vy final is equal to minus 16.765 meters per second. Because it's going to be going up this speed when it starts. When it launches or when it ends, it'll be the same speed in the opposite direction. And I could have used Vy final is equal to Vy initial plus Ayt. So And you can see that those are 16.765 times 2 is the same as 16.765 plus 16.765. So those do give us the same answer. So it's going to be in the air for 3.42 seconds. Then we come over to the x component, and I can find the range easily just by saying my initial position was 0, my acceleration in the x direction was 0, and so that's just going to be 29.04 meters per second multiplied by the time we just found. Well, that was 3.24, right? 3.42. And so the distance we're going to get is 99.3 meters. Now, how many sig figs do I have here? I believe I only have 2. And so we'll just put to correct sig figs. 99 meters is the distance it will travel, and the time to 2 sig figs, 3.4 seconds in the air. 99 meters, that is much more than the 10 feet they needed to clear. Or when that thing fell down, let's say maybe it doubled to 20 feet, still much far beyond. If they'd actually had that car going 75 miles per hour and hit the ramp, and the ramp was really 30 degrees, it would have been a long flight. It's kind of fun to do, right? And we now have the tools to do it. Any questions about all of this solution here? Oh, yes, Mira.
I'm just curious how their answer and your answer are identical, just off by a factor of 10. I'm just
okay, let me go back. Their answer was 0.34 seconds. I got to go back and look at this. The X is actually. I don't offhand. Oh, let's just do, I think maybe they did the calculation wrong. I think their work was probably right. The calculation was just. I did the calculator wrong myself. Well, sine of 60, big number. By big number, I mean it's 0.866. Yeah, in fact, they did. They're just, the number that they got here should have been 99.35. And so that's where their answers were wrong. It was, that number there was slightly off of the calculator. Well, okay, going to the lecture, because, got to start with that at some point in time. I told you to go to the right one. So we've done a problem here where you use the range equation, and we saw in class last period, which was Friday, that you have, you can undershoot or go to a smaller angle or a bigger angle, and it'll shorten the distance. And the maximum range is 45 degrees if you start and end at the same elevation. That's general physics assumption that there's no air. Baseball. I pay attention to baseball sometimes, especially when my A's are actually winning games like they've been doing since the All-Star break. Actually, since a few weeks before the All-Star break. you talk about hitting a baseball, the red line is the one that we've been calculating for class. The blue line is real life physics. Now, I'm not trying to teach you fake physics here, but we're making the assumption that the air isn't going to affect the flight of an object, just like we made that assumption with the car. With the car, it's probably, well, if the car's going 75 miles an hour, we know the air does make a big difference. If the car was going 10 miles per hour, it wouldn't make much difference. But you see, it makes a big difference here with the baseball. A hit that clears the fence, if the fence had zero height, at 397 feet in real life would have cleared at 571 feet back. Air makes a big difference. Golf, same thing, except for the opposite. So let's talk about what's going on here and then convert it to the golf. What's the difference in the blue trajectory and the red trajectory? There's a lot of things, just point them out.
The actual trajectory goes higher than the vacuum trajectory.
Okay, the actual trajectory goes higher. The airflow around it is going to be converting some of its forward motion, and in this case, and I think it is looking at, there has to be some spin effect here. So it's raising up a little, and you notice it's not symmetrical anymore. It's kind of squished. So it's falling more vertically than it was rising. That's because the air resistance is slowing it down. In our vacuum, the horizontal speed stayed constant the entire time. But in real life, the horizontal speed has to slow down because of air resistance. And so that's why it has that non-symmetrical shape. And so you can see a lot of physics calculations for baseball with that link there if you're interested. If you have a golf ball and you hit that golf ball, first thing you notice about golf balls is golf balls don't have a nice smooth surface. Why don't they have a smooth surface?
So they can slow down?
Not exactly. In fact, it's kind of the opposite. You said so they can't, right? Yeah. Those dimples make it so when you hit the ball and it's spinning, air is like trapped in those dimples. And so the air that's touching the golf ball is stationary. And as the golf ball spins, you have air-on-air resistance around it. The air-on-air resistance is much smaller than the air on the golf ball skin would have been. And so it's making so you have a smaller air resistance because of what's rubbing against what. Now, because of the spin, you have this thing we call the Bernoulli effect that says if you have a difference in speed, well, the higher the wind speed, the lower the pressure. And so because of the spin, it turns out you have a lower pressure on the top of the golf ball and a higher pressure on the bottom. And that pushes the golf ball up. So a golf ball trajectory, when you hit a golf ball, you actually start with it low because of this effect. And then because of that spin, it goes up like this, and it drops almost straight down. So the golf balls don't travel if you're a good golfer. If you're a bad golfer like me and you don't put any backspin on it, oh yeah, it'll roll forever. But if you're good and you put a lot of backspin on, you drop it, it stays pretty close. If you put extra spin, you can get it to draw back for you. So sometimes you want to hit the top part of the green and draw it back. So those guys are so good, they can hit it, give it a little more spin, get it to come back for them. Me, I'm just lucky if I'm anywhere within 100 yards of the pin. Yeah, that's why we don't go golfing. So they get a lot of extra distance because they start with a really high horizontal component of their velocity, then they convert that into more time in the air, and you actually get a much greater distance with the golf ball with backspin and dimples than you ever would have had if you were just hitting a smooth golf ball. So there's a lot of physics that goes into these sports. You don't think of it if you're out there playing, but in this class you learn that those things exist. Oh man. I put here a problem. Yes, James.
Going back to the last one, if the angle is greater than 45 degrees, would the actual trajectory be lower than the vacuum trajectory? Because then the y and the x would be
no matter what angle you hit it at, it's always going to have this asymmetry for the actual that makes it so it falls shorter. So it's always going to be shorter in real life if you're hitting it, regardless of the angle.
But with like the actual, it actually goes above the vacuum for a small bit. At 45, would it not?
I don't know enough to answer that. Good question. DJ.
Just for my conceptualization, if you're in a vacuum,
Mhm.
is spin irrelevant to...
Spin will be irrelevant, yes.
Okay.
Okay, now I have a time quandary because this problem is a much harder problem. It's one of your homework problems. I think I will go ahead and do it. I will do it for a number of reasons. One is I want you to see how a hard problem of this variety is done. Number two, there are two correct answers for this. And when you put your answer in, what they did is they took the average and gave you an uncertainty that allows either of the correct answers to work, which means that you're likely to get the right answer if you're in the ballpark. But I want you to see that there's actually two correct answers because it just gives you one answer and you're like, but I did it right and that's not my answer because they gave you the average between the two correct answers. So let's do this. The free throw line is 4.57 meters or 15 feet from the basket. So we're going to have somebody at the free throw line. And here's where the basket is. And the basket is a height of 3.050 meters above the floor. A player standing on the free throw line throws the ball with an initial speed of 7.157 meters per second, releasing at a height of 2.44 meters. Above the floor. I want to change the color of my pen. I'm just worried that I'm going to screw everything up by messing with these things. So the trajectory is going to be going something like this. And we have the final variable so there I've written out all of my variables. And I am asked, what angle does he have to shoot at to make it in? You have to sit down and say, how do I start this? And the answer for a trajectory problem is always going to be the same as I just did. Break it up into its components. So I'm going to start by making the x and y components. And in the x direction, I have x initial equals 0, x final equals 4.570 meters. Oh, before I do x and y, what do I have to do that I didn't do? It's required. I have to define what x and y mean. In my brain, I always use x for horizontal and y for vertical if it's two-dimensional. But without writing that down, x and y don't actually carry meaning. So I have my x and y defined there. Vx initial is equal to, it wasn't given to me, but I know using trigonometry, V0 cosine of theta, where theta is what I'm looking for. And ax, what's the acceleration in the vertical or in the horizontal direction? 0. Y direction, y initial is equal to 2.440. Y final is equal to 3.050. Vy initial is equal to v sine theta. And ay is equal to minus 9.80 meters per second squared. Or I'll put equals minus g because it's just shorter to write minus g than write minus 9.80 meters per second squared until I get to the end. Now, of course, I wrote this on the slide. I put this in the other document so I'd have room to work it out because I don't have room to work it out here. Let's quickly talk about what I'm going to do before I go to working it out. So what am I going to do? How am I going to approach this now that I've broken things down into their components? Using as a guide what I just did in the previous problem, what should I do next? Okay, I should figure out an equation to solve for. Okay, theta is my ultimate goal, but if you look here, I have two unknowns. Two unknowns. I don't know time. Whoops. And I don't know. Whoops, not the V initial. I know the V initial. I don't know the angle. So I have two unknowns. So I can't solve either one of these. Theta appears on both sides, and time is going to be in both equations. I can't solve this with just one equation. I'm going to have to solve both sides of the equation and substitute putting them together. And so because I have all of the variables, in both cases, I'm going to use the same equation for both sides. I'm going to have there's my x equation. First thing I do when I solve these is I set zeros to 0. So I put an arrow through my x0 to 0, an arrow through my ax to 0. Now I have a simple equation. X final is equal to Vx initial t. So if I solve that for time, now you might say, why did you solve for time, sir? There are two unknowns. The one I cared about was theta, so I solved for the other one. So I'm going to substitute that into the second equation to eliminate the variable I don't care about, time. So now that I have my x direction done, I turn to the y direction. Once again, I will set my zeros. Done. There's no zeros in this equation. Next, I will substitute in my equation for time, and I will substitute for Vx and Vy. So substituting in my equation for time and substituting for Vx and Vy, I get Vy initial is V0 sine theta. Multiply that by time. Time is x final. Let me change colors just so it's clear that I'm putting in. Great. Vx0 is V0 cosine theta.
What is the XF?
XF is the x final, 4.570 meters. Right there. Putting in my time squared now. I have this equation. There's one good thing. The one good thing, okay, it's not all that great. Neither is my use of the pen here. The one good thing is that the V0 is going to cancel here. Yay. The bad thing is this leaves me tangent theta times x final for this term. Right, sine theta over cosine theta is tangent theta. And 1 over cosine theta squared over here. Now I have to go to the next, well, I wish there was an easy way to do this. It would have been easy if I would have started here and done all of my work here. So I'm just going to continue my work here. So I have That's the equation I had on the preceding page. And anyone with a modicum of brain says that's tough. I have a tangent theta, I have a 1 over cosine squared theta. The unknown here is theta. That's what I'm looking for, but how do I solve it? And so this takes some creativity. One over cosine squared theta is equal to tangent squared theta plus 1, I believe is the correct equation. To make sure we're clear on that, I'll show you the derivation for that. That's a definition. Cosine squared theta plus sine squared theta is equal to 1 for all thetas. So if I divide every term by cosine squared theta, that's 1. And this is tangent squared theta. So tangent squared theta plus 1 is equal to 1 over cosine squared theta. So what that allows me to do is get an equation that is 0 is equal to oops. Or rewriting this in the most provocative form. Notice I changed the sign of everything. So change the signs of everything. Why is that the most provocative form? It's a quadratic. Yes, we have to use the quadratic. So now I set this here is A. There's that minus sign. So this x final, B is minus x final. And then this here there's my A, B, and C. And so using the quadratic equation, I put in those values for A, B, and C. You can get numbers for A, B, and C because we know everything that's in those. And when you put in the numbers, it will give you not one, but 2 values for tangent theta. And then you do inverse tangent, and it gives you 2 angles. And so you have 2 correct answers. They're only different by 2 or 3 degrees. And as I told you, what the textbook or what the website uses is the average between the 2. So I'm going to leave the final calculation to you, but I wanted you to see this is how the hard problems work out. Now, what will you see on the test? You won't see one that's this difficult. But if you can do one that's this difficult, then you should be able to do the ones that you see on the test. I've totally run out of time, Sarah.
So the B initials canceled out on the first part of the equation?
Yes.
But what happened to the B initial?
Did I drop it off? That would be an error then. That should have been, it should have been right there. and probably has the same problem because I know I went from memory going from one page to the other, and I probably messed it up there as well.
So that last, the initial square does not drop off at all?
Right, it was actually correct here. This one here stays there, yes. This here should stay. Right, I made a mistake when I transferred from one page to the other. I'm glad you pointed that out, or everybody would have gotten the wrong answer, said, what? I took the final equation he had. Okay, we're out of time. We didn't start physics. We didn't start dynamics. This will be the last lecture covering material that will be on the first exam. The Newton's laws is not on the first exam. When is the first exam? Tuesday. Here in this classroom at 2 p.m. All right, have yourselves a great hump day. I'll see you on Friday.